In this presentation, I want to go over how to approach a kinetic analysis. Now that we're in the branch of mechanics called kinetics, the study of forces causing movement, we will want to do a kinetic analysis. And these are some important points. There are some important points to consider when doing a kinetic analysis. First and foremost, you need to determine which object or what object or system of objects you're interested in analyzing motion of. Then you need to identify all the forces acting on the object, on the system. And I'll explain what I mean by system as we go through this. Know that for every force acting on the object, there's an equal and opposite force created by the object. We're not going to concern ourselves with those forces in our kinetic analysis. We may ultimately be interested in those reaction forces, or excuse me, we may be interested in those forces created by the object. But for our kinetic analysis, we're only going to be identifying forces acting on the object. Again, I'll explain this more as we go along. Once you identify all the forces acting on the object, you then apply Newton's second law, which is add up all the forces acting on the object. I gotta take that dash out, looks like a minus sign, which it's not. Apply Newton's second law, add up all the forces acting on the object, and that equals the product of mass of the object times the acceleration due to the center of mass of the object. Mass, remember, is a measure of an object's inertia, with inertia being resistance to change motion. Okay, then we're going to break the analysis down to specific directions. And what I mean by that is horizontal direction, a vertical direction, or medial lateral direction. We'll stay with those linear directions, descriptors of movement for this as well. So we would add up all the forces acting on the object in the horizontal direction, all the forces acting on the object in the vertical direction, and add up all the forces acting on the object in the medial lateral direction. And we choose one of those. Typically, we'll do one at a time. And realize that the kinetics, the forces causing motion, are directly related to kinematics, the study of motion without concern of the forces. And the magnitude and the direction of the forces will influence the magnitude and direction of the acceleration vector because of F equals ma. All right, so we'll take this approach with any sport that we're interested in understanding, whether it's something as simple as a counter movement jump, whether it's something as simple as running or biking or swimming or biking uphill, or maybe something more complex like some dive or some artistic maneuver. But in each of these cases, what we're going to do is identify a force acting on the object or the system. In this case, we may be interested in the bike rider system. We'll consider the bike and the rider to be one thing, as opposed to just the biker, or as opposed to just the bike. All right, we'll identify the object, the system that we're interested in understanding, and then we'll identify the forces acting on that object, not by the object, but on the object. Now, a place I always like to start is with projectile motion. And the reason why I like to start with that is if we take all the air out of the room, we only have one force acting on the object, and that's the force due to gravity. If we leave air inside the room and the object is moving through air, air is in essence considered a fluid in that case, and it would provide a resistance to movement. And we know this. If we're driving along, we stick our hand out the window, we can feel that air resistance, that air pushing on the hand. The air in essence acts like a fluid, and we can calculate the drag force. And so even if we concern ourselves with two forces acting on the object, we have an upward force if the object's falling downwards, being drag resistance force, and a downward force representing gravity. And in the horizontal direction, however, we really don't have any other force. We could consider air resistance in the horizontal direction, but if we take all the air out of the room, there would be no resistance in the horizontal direction of the movement of the object as well. Now, what's interesting is if I do take air out of the room and we drop the object, we will actually see that the object will accelerate at negative 9.8 meters per second every second, meaning it's getting faster and faster and faster at a rate of negative 9.8 meters per second every second. So if we start here at this object with an initial velocity of 0, after 1 second, it should be traveling negative 9.8 meters per second downwards. We go another second, then we go another negative 9.8 meters per second downward. So we would be at 19.6 meters per second. If we go another second, another negative 9, and so forth. It's going to continue to speed up while moving downwards. Now, interestingly, when we push this object off to the side, when we're dealing only with the vertical dimension, that object will accelerate the exact same way as if we just drop the object when we're dealing with one dimension at a time. Okay, so the yellow ball, if it's shot off perfectly horizontally, will hit the ground at the exact same time as the red object when that object's dropped from a 0 velocity. I've got some other videos on this, and it's really an interesting phenomena. But the point of this slide is to really nail down the idea that we're going to deal with one dimension at a time and not concern ourselves with multiple dimensions at once. So if we're interested in the vertical dimension, we'll only analyze the vertical motion, and we can do that because the different directions of motion that we're dealing with, vertical, horizontal, medial, lateral, are orthogonal to each other at 90 degrees to each other, and so they end up being a bit independent of each other. Okay, so just emphasizing that point, both balls fall vertically at the same rate. The yellow ball moves horizontally because it was given some initial horizontal velocity. But I've got another video talking in more detail about that. But in any case, in doing a kinetic analysis, we identify the forces acting on the object, and those forces will explain the motion of the object. All right, so we'll do that with more complex movement beyond a projectile motion. We'll do someone jumping. Still pretty simple, but more complex. But now we have two forces acting on the person. We have the force due to gravity pulling the person downward, and the force of the ground pushing up on the person. Notice both of these are forces acting on the person. Now the person is moving through air, but the air will have very little influence on this type of movement. So most of the times when I do this problem, I'll neglect air resistance because it's such a negligible force. It's so small that it's not really going to influence what's going on. Okay, so once I have those two forces acting on the person, I then put them in the equation. Sum of forces acting on the object equals ma. And we can understand this person's movement perfectly by knowing the forces acting on the object. Now know that as someone may be interested in help someone train to jump higher, I'm actually interested in the forces created by the person, how much pushing the person's doing on the ground. Realize that what the person's doing is an equal and opposite force, the ground reaction force is equal and opposite to what the person's doing. And we call this the ground reaction force. It's the force from the ground in reaction to what the person is doing. The person is pushing on the ground is pushing back on the person. So to understand what forces the person's generating, I actually measure and analyze the reaction force. It's too hard to put force sensors inside the muscle to actually measure that, but this force is equal and opposite to what the person is doing, both during jumping and during landing. And when I do measure the ground reaction force, and I do that fairly simple, I have someone stand on a special device that is nothing more than your bathroom scale. And your bathroom scale, measures how much force gravity is pulling down on you with. And as long as you stand still, that bathroom scale will settle on a particular number, and that's your weight. Well, if you move while you're standing on that bathroom scale, the dial of the scale will change, or the number will change if it's a digital one. Well, we have special force platforms that cost $10,000, $20,000 ultimately installed, that measure all those deflections of the scale as you move on the scale. And so that's what this is. This is a ground reaction force on the y-axis and time on the x-axis, with 0 being the moment the person leaves the ground. And now we can start trying to understand the forces created by the person by measuring the reaction forces, both during jumping and during landing. We've got some other videos on the ground reaction force during jumping as well as during landing. And we can learn a lot about the stresses placed on the person, as well as not only the physiology of how much muscle needs to contract to cause a jump, but also technique. In this case, this person's been instructed not to use his arms. Well, using arms is actually a really interesting phenomena that can influence this ground reaction force. Or if you jump using both legs at the same time versus a one-legged jump, which you would use a lot of times in maybe a layup of a basketball shot, or even in a high jump in a track and field event, you would be jumping from one foot, or springboard diving or things like that. Right. So in any case, we can understand what's happening by the person by measuring the reaction forces. I'll have some other videos to go more in detail on that. And this continues, this idea, this concept continues. We can look at running, and we can look at the forces acting on the runner. In this case, I've got air resistance, I've got gravity, and I have the ground reaction force. And it's important to know the ground reaction force is a three-dimensional force. It acts in 3 directions: vertical, anterior, posterior, and medial lateral. But we'll typically just analyze one dimension at a time. And I did add air resistance in here because it can actually be a real force when, especially if we're running outside into a headwind or assisted by a tailwind. And that there is some interesting effect that the air resistance has during running. And if you're running a pack, you can actually gain some advantage by drafting off of another runner, but you have to be really close because this force is not that big, but it's big enough to actually keep in mind as we do our kinetic analysis of running. It can be, the analysis can be more complex than that. For example, looking at biking, what we need to do is we need to first identify what system we're interested in. And I've got a graph here, or illustration of a bike rider system. And when we treat the bike, the bike and the rider as a system, then we just identify forces acting on the system, not by the rider. So I've got air resistance, which we know is a key force, air resisting force during cycling, because the cyclist is moving much faster. And we'll actually learn that this force is partly a function of how fast the fluid is moving over the object. I've got gravity here, and then I have ground reaction force here and here. And then I've got this other force here, and we'll learn more about this, especially if you take KIN 656, Biomechanics of Endurance and Performance, where we look at resistance to rolling. And then finally, I have actually the propulsion forces all the way back here. This is what's driving the bike rider system to go forward. Notice I don't have any forces on the person in terms of the foot or the hand, or this could be the elbows or hand, or even the seat. Not when we're dealing with the bike rider system, we're taking this whole thing as one object. Now, if we did want to break it down into, I've got a slide here. This propulsive force, what's really interesting is it has to match the resistance forces in order to maintain velocity during cycling. So you want to have these resistance forces as little as possible, and that means you need as little propulsive force as possible, which means you can maybe bike for a longer period of time with reduced drag resistance force. And so really, cyclists especially really work to reduce the resistance forces acting on the system. Now, if we were interested in what's going on with the rider, well, now we have some other arrows to deal with. We still have gravity, but the gravity acting on the person only, as opposed to the bike person. We have a push on the seat. We have a push from the pedal onto the foot. We have a push of the elbow pad onto the elbow, push of the handlebars onto the hands as well. And then we still have an air resistance force here. But these are still all forces acting on the person. And I may, for some reason, be interested in knowing these forces. So I can put a transducer on the pedal and measure how much force the person is pedaling with, or maybe even a transducer on the elbow to figure out how much weight the person is pushing on the upper body, things like this. And then you can manipulate the fit of the cyclist to maybe minimize some of these forces or maximize some of the forces. But again, step one of a kinetic analysis is know which object you're really interested in understanding. Also realize, as I said, ground reaction force is 3 dimensions, and sometimes we're interested in a component of a force. So riding uphill, we have to, and I'll have additional videos on this. We have to take that ground reaction force and decompose it into a force that's parallel to the surface and one that's perpendicular to the surface. And this because gravity is a force and it is a vector. It's represented by magnitude and direction. And if the direction of movement is riding uphill, I need to concern myself with that resistance force going uphill. And so we break that gravitational force into the parallel and normal or perpendicular to the surface component. Yeah, and so this is why bikers really like to reduce the weight of themselves and or the bike in order to have as little resistance force going uphill as possible, or at least to minimize it as best as possible. And we know that that slope force, the reason why it's getting harder to bike up a steeper hill is because that component of gravity that is parallel to the surface gets bigger and bigger as we get a hill that's steeper and steeper. And this force is resisting the person riding uphill. Now, clearly it would be aiding the person when they're riding downhill, but I've mostly concerned myself with reducing the resistance force and biking uphill. All right, again, just to emphasize, when we do a kinetic analysis, that we need to identify forces acting on the object, and we need to know which object we're interested in. If we deal with this lifter and we deal with the lifter weight as one system, then we have gravity acting on the system, which would be the person's weight plus the weight of the weight being lifted. And then we have the ground reaction force acting on each foot. Notice I don't have the hands. A force is applied at the hands because I'm only concerning myself with the lifter weight system. Again, critical step in the kinetic analysis. If I am interested in the weight or the person, I need to do a different kinetic analysis. In this case, if I am interested in what's happening kinematically with the weight, I would identify the forces acting on the weight. And that would include gravity and the weight, the force of the hands pulling on the bar. Okay, I'm identifying forces acting on the weight. I add those up, and that equals to mass of the weight plus the bar times the acceleration of the center mass of the weight. All right. Again, kinetic analysis, you got to identify the object. What's also important is if I am interested in the weights, kinematics, and understanding forces acting on the weight, I need to be sure to account for all forces acting on the weight. In this case, this person's added some links of chain to the bar, and as this person moves upward, there's more links off the ground, and therefore more pulling force being applied to the bar by these links. And if I do my kinetic analysis, I have to account for that force. And something that we have to deal with a lot of times is making sure that we can measure all the forces acting on the object. So if this is the object here, this little red football player, I got to identify all the forces from all these other players acting on that person, including the ground and gravity. And same thing here, to understand this person's movement, I need to understand the force of this person pushing on that person, as well as ground. And same thing here. All right. So it can get a little complicated when we start doing whole body movements or movements during sports, because we have to always be on the lookout for any pushing or pulling on the object. And then when we add up all those forces, all that pushing and pulling, we can ultimately understand that person's movement. Swimming is just another example. If we're interested in the swimmer's movement, we have to identify a drag force due to the water moving over the object. We have to identify a buoyancy force pushing up on the object. We have to identify gravity pulling down on the object. We have to identify a resistance force applied to the hand, which ultimately creates propulsion. And then there's also a lift. That's another funny component of drag force. But notice in all these arrows, they're all forces acting on the object, not forces created by the object. All of these forces are on the object, and we add up all those forces, and we can understand that person's acceleration. All right, so it can get a little bit more complex, but the concept is the same, is that we're always identifying forces acting on the object. And so then we, in this example, we could start looking for ways to reduce the resistance to moving forward through the water. So we start looking things at swimsuit, or how the goggles are shaped, or the cap, or the skin, or even the body position, because we're interested in factors that would influence this drag resistance force. And then we also want to try to maximize the propulsive force by doing a particular type of technique with the stroke, or having hand position a certain way. And these are some of the details that we can get into when we start doing a kinetic analysis of swimming. But it all starts with identifying forces acting on the object. This kinetic analysis can actually get quite complex. And I put this in here because as we start doing aerial maneuvers, there's some turning, there's some rotation. So now we have to deal with angular kinetics. And so we've got another we've got linear kinetics that we go through, then we go through angular kinetics, and then we try to combine those worlds to try to understand complex movements like a dive, in this case, 1/2 forward with a 1/2 twist. And we'll learn things about angular momentum, angular impulse, and how these tasks ultimately are done. But it still starts with a kinetic analysis, identify the object that we're interested in, and identifying forces acting on the object, not by the object. All right, just to summarize, just as I said, determine what object or system you're interested in analyzing, identify the forces acting on the object. Know that we may be interested in these forces that are in reaction to what the person, or not person because we're doing human movement, is doing. So if I'm interested in how much force the person is creating during a jump, I actually measure the reaction force, which would be the ground reaction force. Then we apply Newton's second law, and then we pick a specific direction to do our analysis. Analysis in horizontal, vertical, medial, lateral are the 3 dimensions that we'll stick to. And then I'll end up with 3 equations. So if I'm interested only in horizontal motion, I only concern myself with the forces acting in the horizontal direction. Likewise in vertical, or likewise in medial, lateral. And finally, the kinetics are directly related to kinematics in magnitude and direction. Okay, so that's a big picture in terms of the kinetic analysis. I hope that's helpful. Thank you.